Alright, so say that you have a test tube, and you know for sure there are a whole bunch of different DNA fragments in that tube. What you want to know is whether all those DNA fragments are the same size, or if there are different sizes. The way you can figure that out is by performing gel electrophoresis on this sample. And so basically the way gel electrophoresis works is that it separates molecules out according to their size. And so to see the idea behind this, how about if we just assume that in this test tube are a whole bunch of different DNA pieces, but they're all just of three sizes, kind of like this. So there are some that are really big, there are some that are the exact same size but they're of a medium size, and there are some that are teeny tiny. And so to help us visualize what's happening to these different size fragments, how about if we color code them, kind of like this, so that the biggest pieces are black, the medium pieces are purple, and the smallest pieces are green. The way we visualize that there are actually three different size fragments here is we load the contents of this test tube, which is all of this stuff, into an agarose gel, kind of like this. And the place in the gel where you load it is this little divot or well. So let's just say that we load everything in our test tube in this well right here. And remember, we color coded it so that all of the big pieces are black and the smallest pieces are green. In order to visualize the different size pieces that we just put into that well, what's done is that an electrical current is run through the gel. And the way the gel is set up, it's set up so that there's a positive charge or positive end over here, and then a negative end over here. Keep in mind that if you consider the structure of a DNA molecule, its backbone contains phosphate groups. And remember that those phosphate groups have a negative charge to it. So because the DNA molecule has a negative charge, in this setup, they should migrate towards the oppositely charged end, which is the positive end. And so that's what you'll see happen if you let this sit for a few minutes, is that those DNA fragments will start moving towards the positive end. It turns out, though, that not all of the DNA fragments will travel at the same rate. The biggest ones will kind of have the hardest time maneuvering their way through this gel. The smaller compact pieces will have an easier time moving their way through the gel. And so if you could actually see these fragments move over time, what you would see is something like this. And so at the end, if you were to see the gel and you see three bands like this, again, basically what this tells you is that whatever you loaded, or the sample that you loaded into this well, contained three different size DNA fragments. Some that are really huge, some that are medium, some that are really small. One thing to keep in mind is that as you're looking at these bands, what these bands are comprised of are thousands of DNA fragments. So for example, this band right here, the green one, that contains thousands of DNA fragments. They just happen to be all the same size. That's why they traveled together as a pack, or as a band like this. Right, so same thing here. This band over here contains thousands of DNA fragments, but all of those DNA fragments are relatively big. And you can tell that because they were barely able to move out of the well as compared to, say, the fragments that comprise the green band. All right. So to kind of hammer home that point, suppose that you loaded a different sample into this well and you let it run over the same period of time and you see something like this happen. Basically what this tells you is that whatever sample you loaded into this well, they were all the same size. You can tell that because there was only one band. Not only that, but you can tell that the DNA fragments that comprise this band are all really huge because they were barely able to get out of the starting block. Again, to hammer home the point, if you loaded a different sample into this well and you let it run for the same amount of time, and you see something like this happen, that'll tell you that the sample you loaded into this well contained 6 different sizes of DNA fragments, and they were all relatively small because they were all able to run pretty far into the gel during that same time period. One misconception that people commonly have when they're first interpreting gels is this. So it turns out that the position of the band on the gel tells you how big or small the fragments are, and not the size of the band itself. So here's what we mean by that. So say that you loaded a sample into this well, and you ran it the same amount of time as the sample that you loaded into this well, and you see something like this happen. The way you would interpret this is this. Well, you see that the fragments in this band traveled the same distance as the fragments in this band, right? They're equidistant from the well. What that tells you is that the fragments in this piece and the fragments in this piece, they're all the same size. The reason why, or one of the reasons why, this band is brighter, bigger than this band right here is because there just might be more of those DNA fragments in this band versus in this band. All right, so again, the bottom line is that if you want to know how big the pieces are inside of a band, look at how far it traveled out of the well. If you want to know how many pieces of DNA are inside that band, you look at how big it is. So there are more DNA fragments that comprise this band as compared to this band. All right, so again, by looking at these results up here, say, you can tell the relative sizes of the DNA fragments that comprise each band. Right? So there's big, medium, small. If you want to be more specific as far as how big the pieces of DNA are that comprise each band, what you need to do is run a molecular weight standard. And so here's the idea behind that. Molecular weight standards are, you can basically buy these from different companies, and what they are, it's a test tube that contains known sizes of DNA fragments. So the company that you buy it from will tell you, hey, this test tube contains DNA fragments, and each of them is, for example, this size. Because you have known sizes then of DNA in your molecular weight standard, if you load it onto a DNA gel, say this well right here, and then run it, because you know the sizes of each one of those bands, what you'll be able to do then is if you run a sample alongside the standard, a sample containing DNA fragments of unknown sizes, you can use this ladder here in order to estimate the sizes of the fragments, for example, that comprise this band. And so you can see that the fragments in this band traveled somewhere in between 730 and 650 kilobase pairs. So you can estimate that the fragments that comprise this band are about maybe 700 kilobase pairs long. Same idea here. The fragments in this band are just a little bit smaller than the fragments in this band, and you can tell they're smaller because they ran further into the gel. So you might be able to estimate that the fragments in this band are maybe about 100 kilobase pairs long. One last thing to mention about gel electrophoresis is that keep in mind that in real life, DNA molecules don't really have a color to them. So typically what you have to do in order to visualize the band is that either at the end, you can stain the gel with something that specifically colors the DNA bands, the DNA molecules, or at the beginning, before you run the gel, you can put something in the gel that will stain the DNA molecules as you go, so you can just view it at the end. All right, so the basic idea behind DNA gel electrophoresis.